Thank you very much. It was a great setup. And I'll jump right in.
I'm not sure if your microphone's on. There you go.
How's that? Better? All right, great. All right. Well, thanks, Sarah. So let me pick up where Sarah left off. And so she finished her talk by setting out this conceptual framework of the functional flow components that were as sort of the foundation of our approach that we're proposing for California. And so what I'm going to do in the next 11 minutes that I have left is sort of walk you through how we take this conceptual model that Sarah laid out with the sort of the functional flow components over the annual hydrograph, and how do we then translate that to a set of numbers or a process that managers can use to actually begin making decisions about how to establish flow targets and how to determine whether those flow targets are being met or not in actual implementation. Now, this is a challenge in a state like California. These are maps of the state of California just showing you a little bit about the complex geology, temperature, and precipitation patterns we have across the state. So we often say we have continental scale variability in the state of California, and that translates to an incredible diversity in our stream network and the types of processes that occur there. And so what I want to share with you is how we take these conceptual models and apply them in a very complicated setting. However, it's important to note that California is not unique just for fun. I went on the internet last night and pulled up some maps from Japan, because here we are in Japan. And you can see that these types of sort of spatial heterogeneity is not something unique to California. California is a little bit bigger in terms of land mass than Japan, but we have these similar types of issues. And so I think these concepts apply across settings where you have this complexity in the landscape. And so, coupled on top of this complexity in the landscape, not only does it lead to a diverse set of stream types, as you can see in the top set of photos here, but we have a diverse set of management challenges as well. And so in some cases you might have dam operations, such as the examples that Sarah showed, but in other areas, such as we might have agricultural production and return flows and groundwater extraction associated with agriculture. In some areas we might have urban water uses, including for those of you who live in dry climates, a much more emphasis on recycled water use now, which again fundamentally changes the way water is used in the system as we discharge less into our rivers for the case of recycling. And so all of these challenges are sort of coupled on top of the complexity of the landscape. So how do you take that sort of challenge of complexity and turn it into something that a manager can use? So as Sarah alluded to, in California we're promoting this tiered framework. And when we start to sit down with the managers and ask them the question, what do you actually need? So what can we as scientists give you in terms of a set of tools or a set of numbers to help you make decisions? As some of you may have experienced, they often don't have an answer to that question. But it's an important question to ask, because asking the question sort of starts that dialogue and helps them start to think about what do they really need to make those decisions and how can we ensure that our science feeds into that decision-making process. And one of the interesting things that we heard from the managers is we know there's a lot of complexity at sort of the basin scale or the watershed scale, but we have lots and lots of watersheds in the state of California, and we can't wait decades to establish basin-specific flow standards for all of these watersheds across the entire state. We need something that we can apply at a statewide scale as a starting point. We need a place to start that we can apply universally across this diverse landscape to just give us our first baby step in this direction. And then we can come back and we can do some of these more detailed basin-specific studies as necessary. And so that led to this idea of this tiered framework, where we would start with something that was more at a statewide scale and importantly reference-based, and I'm going to come back to that. And then we provide that starting framework to apply this functional flows approach at the state scale, and then provide a roadmap or a framework for how to then come in and apply that at a more specific basin scale where necessary. So what I'm going to do is I'm going to walk you through mainly this tier 1 or the statewide approach. I'm going to introduce the tier 2, and then Greg, who's going to come after me, is going to get into more detail about some of the tier 2 tools. And so, as Michael said in his presentation, classification is an important first step, as we've seen in the Aloha framework. And so there's 3 critical components in this tier 1 approach. The first is classification. We've got to take the state of California, very complex, and organize it somehow. Then we have to apply this conceptual model that Sarah laid out, and we have to then turn that into a set of numbers that we can manage towards. And so I'm going to walk you through each of those steps. So the first step was classification. So this is our map of the state of California. And so what we did, very much like Michael talked about, we sort of thought about what are the fundamentally ecologically relevant flow types or hydrologic types that we have in the state of California. So we went through a process very similar to some of the papers that Michael referenced, where we used some statistical analysis based on a set of reference gauges across the state to basically be able to take an understanding of these we identified 9 flow types, and using a combination of catchment properties, rainfall patterns, geology, and soil properties, we can essentially model or predict where in the state each of these 9 flow types would occur based on those catchment properties. So we built this statistical model. So now we have a starting point to say we need to think about environmental flows for each of these 9 classes, somewhat individually or somewhat independently. The second step is that we need to define some targets of kind of what are we aiming for. So we have this concept called the dimensionless reference hydrograph, and it's really important that middle term, the term reference, which I've bolded there, is really critical, because we know that there's a complexity of ecological types across the state, but if we want to develop a set of tools that can be applied across the entire state, we decided that this tier 1, or this first step, we're going to take a reference-based approach. So it basically means that we're going to define a set of targets based on some sort of deviation from reference hydrology. So that's a good starting point. It's not tied to any specific taxa or any specific habitat, but it's a good starting point for a large spatial scale like the entire state. So we define these dimensionless hydrographs. Let me walk you through these a little bit because it's sort of a foundational piece of what we've done. So this is our snowmelt runoff dominated system of those 9 classes. And what we do is we look at all of the reference gauges that occur within that specific hydrologic class. And we look at the daily flow for every day of the year across the entire period of record. So if we have a 40-year or a 50-year period of record, we look at the daily flow. And then we take that daily flow for each year, for each day of the year, we divide it by the mean annual flow, and that non-dimensionalizes it. So that's important because it allows us now to compare across types, big catchments and small catchments, on an even sort of scale on the y-axis. But what we get from this is a picture. You can see that the red is the 50th percentile over the period of record, and then we have the 25th and 75th, and the 10th and 90th. So you get a picture of not only the pattern over the course of the year, but how much variability there is within that pattern across the period of record that we have gauging data. So that's our dimensionless reference hydrograph. And so I've showed you, just in the interest of space, I have 7 of our 9 hydrologic classes here. And just what I want to impress with this slide is the incredible amount of hydrologic variability in the state. And so if you just look at these, you can see that those classes are very different in terms of the patterns that they have over the year. And if you look at the y-axis, you can even see, for example, the snowmelt in the upper left corner there. That x-axis only goes up to 6, right? Which means that those peak flows are only sort of 6 times the mean annual flow at the touch. Whereas some of these more flashy systems, the y-axis goes up to 20, right? So you can see there's incredible variability in the system, and so we have to account for that when we think about how to set these flow metrics. So now we come into the set of flow metrics. This is the same table that Sarah showed you. So we've gone through this process of using the ecological principles that we have and what we know in the literature to identify a set of quantifiable metrics that are associated with each of those flow components that we've identified in our conceptual model. So this gives us a suite of metrics to work with. And so just what I'm going to do is walk you through one example of that to see how you then take that and apply it on the ground. And so we're going to stick with spring recession, which was the same example that Sarah showed you. And so what we have here is now I've given you the same dimensionless reference hydrograph. We're in the low volume snowmelt and rain class, as you can see. The functional flow component that I'm interested in for this specific example is the spring recessional flow. So we've defined the spring recessional flow. And so the green, what you can see is we've bounded, based on that dimensionless reference hydrograph, the range from sort of the 10th percentile to the 90th percentile in terms of magnitude, and the 10th percentile and the 90th percentile in terms of duration. So the box represents a range, a magnitude and duration range for a specific metric, in this case the start timing of those spring recessional flows. So what that means is if you really want to try to manage your spring recessional flows, you need to be sort of in that box. So now we can show that to a manager and say, we have a definition for spring recessional flows, we have a defined magnitude range and a time range, and if you can manage your flow within that box, then you're meeting your target in terms of what we think is meaningful for the ecology in that particular system. So now you can come in and you can take flow. This is a specific, this is a hydropower. This is the South Fork of the American River, the 2013 water year. This happens to be below a hydropower dam, and so the management question has to do with releases from the dam. And so if you overlay that hydrograph, and that can be a measured hydrograph or a modeled hydrograph, we can see that the red dot, based on the definition of the start timing of the spring recessional flow, that red dot falls outside of the box. So we define a range and a magnitude, and so in this case, we can say that we have that spring recessional flow beginning too early and it's too low. And so if you were going to manage the system, you would make adjustments to the system to try to move that flow up into that box. So we can define a series of those for those different metrics, and we can start to develop a suite of metrics that we can then go to managers and say, here are some very defined ranges that we would like you to try to manage within to be close enough to that reference hydrology that is ecologically relevant for a broad set of species. All right. So that's kind of the concept. It's a sort of a lot to assimilate on one slide, but the concept is it's an approach that we can now apply, and because these hydrographs are dimensionless, we can do this across the state on sort of an equal footing. All right, so just to wrap up, that may not get you all the way there. It might be close, but not perfect, right? And so if you need to get into more specificity, that's where we kind of went to tier 2, and this is what Greg's going to talk about here. And so you might say to a manager, okay, that's a good starting point, but your manager might say that doesn't, gets me close, but not quite close enough. I need something that's more specific for the geomorphology and the ecology of my system. I might have some more reach scale environmental flow issues that I'm interested in. And so in that case, we are going to allow us to drop down into that tier 2, that more catchment specific approach, and develop functional flow targets based on that tier 2 approach. And the key elements of that, again, the idea is this is a very complicated thing to do across every catchment in the state of California. So we're developing a guidance document that allows you to step through a process, and that's shown on sort of my right, your left. The guidance document, and it produces a set of products, including the baseline characterization of hydrologic condition in your watershed, some geomorphic classification, a list of the ecological endpoints that are relevant for your stream class, and so that's something we're working on right now. So for different stream classes, which ecological endpoints? Is it fish? Is it birds? Is it bugs? Is it a combination of those? Which are relevant to the stream class, and then how do you define those flow ecology relationships for those stream classes? So if you look at that list of products, it will look vaguely familiar, or maybe not so vaguely familiar, to the Aloha steps that were presented this morning, but just more in a list format. So the idea is we have a starting point for tier 1 that you can apply for the entire state. We have a process for tier 2. We have a set of tools that go along with tier 2 that managers can use to apply and develop flow criteria in their specific catchments. So with that, I'm going to end there. I'll turn it over to Greg, who's going to sort of walk you through some more specific examples of some of the tools that are associated with tier 2.